This is section 16.9 and it's about the Lewis acid-base theory. And one of the things that you have to remember about the Lewis acid-base theory is that it's the more general of all three, okay? More general, because the number of compounds that you can classify as acid or base it's broader. So, and in particular, the Lewis acid-base theory is very useful when you have solvents other than water. Okay, you can still define an acid-base reaction in a solvent, let's say like chloroform, that there is no water at all, and then you can still define an acid-base reaction, a mechanism that goes by the acid-base reaction according to Lewis. So one of the things that we have to remember as well with the Bronsted theory, Bronsted-Lowry theory for that matter, is that a base, let's focus on the base for Bronsted-Lowry, and the base for Bronsted-Lowry pretty much we represent that as just B. And when we have this in presence of water, what we get is a base equilibrium in which you produce the conjugate acid plus OH minus. Now, the reason why this base can accept that proton is because it actually contains a lone pair of electrons that then it can share with that proton and then produce the conjugate acid. So that's pretty much how the Bronsted base accept that proton. Now that is the basis for the Lewis theory. Now here we want to focus our attention on that lone pair, and is the basis of the Lewis acid-base theory, because now instead of thinking of the acid-base reaction as the transfer of one proton, now we are talking about the transfer, not quite the transfer, but the sharing of a lone pair of electrons. Okay, in this regard, since the base is the one containing the lone pair, then the base is the electron pair donor. All right, and whoever is receiving this lone pair then is the acid. So now the distinction is between an electron pair donor and an electron pair acceptor. Whoever is donating the lone pair is the base, whoever is accepting the lone pair is the acid. Okay, so main difference between the Bronsted theory and the Lewis acid-base theory. Well, for Lewis, the acid is an electron pair, correct? So now you, in that regard, you are expanding the number of compounds that now you can consider as an acid. However, for Bronsted, right here, the acid is a proton donor. Okay. However, for the Lewis theory, it is the proton. What is the acid now? It's not the Lewis acid is not the compound containing the proton, but is the proton itself. So the proton is the one who is going to receive that lone pair, those electrons. Okay. So another thing that we have to differentiate between the Bronsted-Lowry and the Lewis theory is that when you have an acid-base reaction, normally for a Bronsted-Lowry you will have salt and water. And well, for a Lewis theory you can also have salt and water, but now we are going to be a little more general in that regard. And initially what you obtain in a acid-base reaction according to Lewis is what we call a Lewis adduct. Okay, and basically it's, if we consider this as your Lewis acid because it will receive the lone pair, then this lone pair would be used to attract that hydrogen, and now you are incorporating that into a larger particle. Okay, so initially this is an adduct. Okay, it's the combination of the Lewis acid and the Lewis base. That's the adduct. Okay, Lewis adduct. Now, one thing that is going to be different in this theory compared to the Bronsted-Lowry theory is that, well, here we don't really have a measurement for the acid constant or the base constant. Right, because those are concepts that we can perfectly apply to water solutions or aqueous solutions. But when you have solvents different from water and you have these different compounds that are not transferring protons, then it's more difficult to calculate those constants. Still, you can kind of predict whether a particular compound is going to be stronger than other in terms of the acidity or the basicity. But here, if you're comparing, for example, ammonia with nitrogen, and you're comparing those as bases, then remember that that ammonia looks like this, and then you are sharing that lone pair. Let's write it differently. Okay, but if you look at nitrogen, then each nitrogen will have only one lone pair. However, the problem here with nitrogen particularly, okay, in the nitrogen molecule that is that you have to think in terms of what is the electron density around that nitrogen. And because each one of these nitrogens are pulling equally, okay, toward themselves, so the electron density that you have around each nitrogen is not that great. Okay, I mean, if you compare that with the ammonia molecule, well, hydrogen and nitrogen, well, nitrogen is more electronegative than hydrogen, so it's pulling from hydrogen always towards nitrogen, so there is a larger electron density around the nitrogen. Okay, and because that larger electron density, then that lone pair that you have here, it's more available, okay, more available for sharing. Alright, so that is not the case here in nitrogen. So that doesn't mean that the nitrogen molecule cannot act as a Lewis base, because the only requirement there is that you have a lone pair available. But it's just that if you compare the relative strength of the ammonia molecule versus the strength of the nitrogen molecule, well, because you have a larger electron density in the ammonia molecule, then the ammonia molecule is going to be stronger as a base than the nitrogen molecule can be. Okay, and one other thing important here, that goes for the base. The only requirement for a Lewis base is that you have a lone pair available to form or to attract or to donate to the Lewis acid. But that means that the Lewis acid have to have room to locate those electrons. I mean, if you have a atom that is already with an electron valence shell full, then there is no room for those electrons. So there is no way that it can accept that lone pair of electrons. So that won't be considered as an acid. So you need the room for that. And you usually have that when you have incomplete octets. Okay? So compounds with incomplete octets are right away you consider that as Lewis acid, whether they have protons or not. And if in the case of the proton itself, then, well, it's not a octet but a duet for the hydrogen. The hydrogen can only accept one pair of electrons. Alright? So if we look in terms of a mechanism, remember the base is donating the pair of electrons and they go to the Lewis acid. The end result when you have this reaction is the formation of a new bond. In the special characteristic of this bond is that, remember, any bond will implies the sharing of electrons. Usually when the normal formation of a compound, those electrons comes, if it's a single bond, then you have one electron from each atom. But in this particular one, when you have a Lewis acid-base reaction, that pair of electrons is coming from one of the atoms. In this case, the Lewis base. Okay, and this new bond, electrons come from one atom. Alright, so in this case we have here boron trifluoride, and boron has an incomplete octet here, so it have room for another pair of electrons. So that's exactly what that lone pair in nitrogen does. And then here, this bond that you have there, that is the new bond. Okay, and we give a special name to that bond. when you have a bond that you form, and that bond, the pair of electrons that you are using in that bond, comes from only one of the atoms, then that is a coordinate covalent bond. And one of the good things about the Lewis acid-base theory is that these reactions, they are not limited to aqueous media, not even a liquid media. So you can have acid-base reactions basically in any physical state. Could be in the solid state, could be liquid state, could be any combination of states. You can always produce that new compound. Well, not exactly new compound, but you can always produce the adopt in these reactions, okay, regardless of the state of the matter. So some examples of Lewis's acid. Ones that are very common are metal ions, okay, especially if they have a high charge, but it's not exactly a requirement to have a high charge, but usually you will see this. And what does the positive charge means? A positive charge in this case will end up meaning that they are electron deficient, whether because they want it or not. I mean, aluminum is pretty comfortable with a charge of 3+. It acquires a noble gas configuration in the electron configuration, but it would be electron deficient nonetheless because it comes from a neutral atom. So you remove electrons, becomes electron deficient. So in this case, water takes advantage of it, and then that aluminum has the capacity to receive those electrons and form those coordinate covalent bonds. All right. Another case that you can have is with substances that have multiple bonds. In that particular case, remember here, for example, for carbon dioxide, each one of these bonds contain a pair of electrons. So a double bond is actually two pairs of electrons. So you may get that and move those electrons completely to one of the atoms. In this case, it's oxygen. And why oxygen? Well, because oxygen is more electronegative than carbon. And if you do so, I mean, you are removing a pair of electrons, so to speak, from carbon. So carbon becomes electron deficient, so we can symbolize that with a positive charge. And then we have now an excess of electrons on oxygen here, so it becomes negative. So here carbon now becomes a target for a base, for a Lewis base, in this case water. So water can perfectly, with the lone pair on oxygen, can sort of attack the carbon here because carbon becomes now electron deficient. So one of the things that you have to do when working with Lewis acid-base theory is, one, well, identify whether a given substance is a Lewis acid, a Lewis base, or sometimes it happens that you cannot classify it as either one, right? So in the first case we have iron 3+, and what you have here is it's a cation, right? And as such, the positive charge means this is electron deficient. And electron deficient means it simply has less electrons than it's supposed to have, because I mean, the iron 3+ comes from the iron, the neutral atom. You have to remove electrons, becomes electron deficient. And because it's electron deficient, then it can perfectly accept lone pairs coming its way. So therefore, this is a Lewis acid. Now we have here methane, this CH4. And if you write the Lewis structure for CH4, we have that. The first thing that we recognize here is that you don't have lone pairs. And with no lone pairs, first thing is not a base. Okay? There is actually no deficiency of electrons. Number one, the hydrogens that you see here are not acidic. And they are not acidic pretty much because this bond is almost non-polar. And almost non-polar because they are right at the cutoff of polarity. Okay, so these are not acidic hydrogens. Right? And because they are not acidic hydrogens, remember, if it's a compound that has hydrogens, and the hydrogen is what you will say is the acid part on that compound, if they are not acidic, then they will not be a Lewis acid. So not a base, not an acid, therefore that's neither. Now here, this is chloride, right? And we can represent chloride as simply the chlorine atom with a negative charge, and then we have actually 4 lone pairs around chloride. The presence of lone pair is all you require to classify that as a Lewis base, so this is actually a base. Same thing happens with ammonia. We have already drawn the structure for ammonia. Okay, this lone pair here, those hydrogens are not acidic, remember that, and the lone pair here is what gives ammonia its characteristic as a base. Hydrogen, well, hydrogen is single bond between the hydrogens, so no lone pairs, so cannot be classified as a base. And actually each hydrogen is perfectly fine with that pair of electrons around the hydrogens being shared between the hydrogens. So no acidic hydrogen, let's put it that way. No electron deficient. Okay, and the reason I use the no acidic hydrogen is because if it was able to release that hydrogen, well, the H plus would be the acid. So the hydrogen molecule is also neither. And then we come here to iron. This is just the atom. Okay, technically the iron atom is not electron deficient because it's neutral. Okay, and technically we don't say that this has lone pairs. So technically the iron atom is neither as well. Alright? So even if you are giving a reaction, you should be able to determine, either because you can detect that on the compound itself, or once you look at the structure of the adduct that you are obtaining there, you can determine which one is the acid, which one is the base. Okay? And sometimes we can just give you or tell you what is reacting with what. So here we have a sulfur trioxide reacting with water, and the question is, well, what is the adduct that is formed between SO3 and water? And in a way you have to determine whether you have which one is the acid and which one is the base, because that, based on that, it will give you what the structure is for that particular adduct. So if you work the structure of SO3, you will end up with this. Okay, and if we fully draw this, then you have 2 lone pairs here and 3 lone pairs in each of the other oxygens, and that might be telling you, well, is this an acid or is it a base? So technically, well, it depends on what you are mixing this with. If you are mixing this with water, okay, and water has its own lone pairs here, well, now which one is the base, which one is the acid? We already know that water can act as both. Okay, water can give you an H plus. In that case, the H plus is the acid, but water can also be the base. But you also notice that in this compound you have a double bond, and whenever you have a double bond, you always have the possibility of moving one pair of electrons from that double bond to the oxygen. So what you end up with in this particular case is that sulfur will become something like this. Okay, you still have 3 lone pairs on those oxygens, and now in the one that you had the double bond with, now you have 3 lone pairs there. But that means that this oxygen becomes negative and sulfur now becomes electron deficient. And now when it comes water, with its lone pair, then these lone pairs come here to form that additional bond. So you end up with oxygen, sulfur, oxygen on the sides. Alright? You form a coordinate bond between the sulfur and the oxygen. And this is your adduct. Okay? Now, what's important to know about this? Well, that's not exactly the formula or the structure for a given compound, but this, through a couple of reactions that also involve Lewis acid and bases, this becomes H2SO4. Okay, technically what happens here is that one of these protons end up in the other oxygen. Okay, the transfer is not quite direct between that oxygen and the other oxygen. That's in other water molecules involved this, but ultimately the product would be sulfuric acid. Do you need to know that particular detail? No. But in terms of how to obtain the adduct and being able to predict what the adduct can be, or if you are being given the adduct to predict which one is the acid and which one is the base, well, that part, yes, you have to know it. Okay? So in review, number one, a Lewis acid is electron deficient particle that will accept an electron pair coming from the base. Therefore, a Lewis base will be able to donate a non-bonding pair. If you don't have a non-bonding pair on that molecule, that cannot be counted as a base. Okay, it's a requirement that you have a non-bonding pair, a lone pair on the Lewis base. The initial product of a Lewis acid-base reaction is a Lewis adduct, in which you are forming a new bond in which the electron pair that form that bond comes from only one of the atoms. Okay, that's what is coordinate. Now, because the Bronsted-Lowry bases, in order to capture that proton during the acid-base reaction, they require to have the lone pair, then all Bronsted-Lowry bases are also Lewis bases. Okay, it's almost by definition, they are all Lewis bases. However, the story is different for acids, because for Bronsted-Lowry, there is a requirement. The acid must donate a proton, and that proton is actually coming from the acid. But in the Lewis acid-base theory, the proton is the acid, not the compound that the proton is coming from. Okay, so that opens the possibility for other compounds that can act as an acid, but that don't have protons. The only requirement there is that there is space to accommodate the lone pair coming from the base. Okay.